Hi guys, so I'm going to take up a question or two that Shire actually asked you guys last week. So typically, because most of your, well, I'm guessing all of you at this point are at least second year students, you probably had your first year fall semester online, which means that you guys know that typically in tutorials, um, I would take up a problem, right? Or Tia would take up a problem. And then if you had any questions at some point, you would interject and say, can you clarify this problem? I'm not sure I understand what you were saying. With the nature of things being online, of course, I don't have that, opportunity to do so. So I'm going to try to almost anticipate the questions students have and slow down at some points, right? And so one thing I definitely notice is sometimes I speak really quickly. So if at any point you are confused when you're watching this video and you don't know why I made a certain step, you can certainly post it in the discussion board and I'll get back to you guys. So the two questions he asked actually, is looking at what constitutes a good estimator in the context of the variance, right? So ironically, this is kind of a funny thing for a couple of reasons. Is that one, you can almost intuitively see that we in statistics are fascinated with the normal distribution and all the things that arise from it, including the chi-square distribution, which we know is a square of the normal. And it also elucidates this notion of the MSE, which is the mean squared error. And in the context of the frequentist approach of statistics, the mean squared error is something you want to keep small. You want to minimize this because it would then tell you your estimator is not only unbiased in some sense if your bias is very small, let's say, or in fact if your estimator is an unbiased estimator, and the variance, because it is actually a function of the bias and the variance. Which is what you're asking this problem. So you're asked, given two estimators for sigma squared, and indirectly you're being asked which one is a better estimator because one of them will have a smaller MSE. So let's kind of look at this. So before I answer the questions, I'm going to almost actually anticipate people will ask, can you clarify what the MSE is? And why are you talking about this notion of a bias and a variance? So I'm going to go to section 3. I kind of started a little bit earlier just because I felt that some of the stuff was, could have been written out before I started talking. But you can see the MSE is actually literally the sum of the bias and the bias grid and the variance, right? So immediately you could ask yourself, is it possible to have an estimate that not only has the smallest variance and the smallest bias, is like making it in some sense the best estimator you can get from the frequentist approach? Can you have both zero bias and zero variance? The first thing I said in the sense that like you could have something that has a minimized bias and and similarly a minimized variance is possible, but having them both small is probably not. It's not actually possible, right? So which means that we're always trying to work with this trade-off. Basically, you want to make your bias small. In fact, you can make it as small as 0 if your estimator is unbiased. But of course, you make your bias small. A lot of times you increase your variance. So there's this trade-off. We're trying to, in some sense, minimize the two. And it's not really a completely perfect optimization problem because there's no actual general solution that will make them both 0. Unless it's the case that your actual estimator is always going to be something that's like a constant or something, right? If your actual theta is a constant, and of course, obviously, the bias and the variance is small, but anything that has a statistical distribution on it, it's you probably have to think about this trade-off. And the question you might ask yourself is, why is this MSE literally the sum of the bias and the variance? And I just kind of did a couple of manipulations here. So in particular, the manipulations are in red, right? So let's check, right, that what I actually said is true. You'll notice that it doesn't immediately fall off from the expression, right? Let me see if I can draw it. It doesn't fall off from the expression here that the bias, that literally the MSE is the sum of these two things. Right? So we should ask ourselves, why does it look like the functional form you see in, let's say, the right-hand side? And to explain this, I kind of put this part in red here that you see, like, so you see that in the next step, I have added and subtracted expected value of theta hat. And this is because when I add and subtract any number, right, I've literally added 0 into my expression. So it doesn't actually change anything other than make it look like something I want to actually uncover, right? So I added and subtracted expected value of theta hat, which yielded for me. So when I actually, this means I can collect my actual terms in such a following way. So I'm going to collect it like this, and then it becomes a quadratic that can actually expand. So that's what I've actually done. You can see that I've expanded the actual quadratic in this next line here, right? And I result in this expression here where the first term that I highlighted in blue is a squared term, obviously. So expected value of this thing squared. And the last term here, right, is also expected value of the expected value of theta hat minus theta. So this is actually, if you follow the formula above, this last part here is the bias, and this part is the variance. Now, you can almost imagine that it kind of looks like what you saw above, but not really. There's something that I have to kind of address. What I should address is the fact that the second part, the middle part there has to be 0, right? So I'm not going to make any claims about this part here, because quite frankly, I cannot say this is 0. I don't necessarily know. It may not be the case that theta hat is unbiased, right? So in which case this may not actually be 0, but we know that the expected value of theta hat, so the expected value of this is actually expected value of theta hat, right? So this is me actually just being the expected value within this part here, right? And expected value of any constant is a constant. So when I put the expected value of this thing here onto expected value of theta hat, it's still expected value of theta hat, which makes this entire part here 0, right? So this part here is then 0, right? Which is what you're seeing. So this is the first question you were asked. You were asked to calculate the MSE of S squared as an estimator of sigma squared. Now, the first thing I kind of will direct people to is the idea that you were actually told that all of your XIs are, in fact, IID. So I'm going to actually highlight this. This is not trivial because you guys know that if you have random variables that are independent, right, the squares of those random variables are themselves still independent. This is an important idea when we talk about the chi-square distribution, because some very nice properties will fall out in regards to computing the variance of S squared, because you can express it in relation to the chi-square distribution, right? So we're going to use the fact that the random variables are in fact IID so that we can kind of suggest that the square of their sums is going to be something that's actually distributed chi, right? Because we know that the sum of these normals are themselves normal because they're independent. So let's remind ourselves of what the estimator S squared is. And you know that S squared is actually the sample variance for data. And we see it, it's so prolific in statistics. We see it all the time. But in case anyone hadn't remembered, it's S squared is equal to the sum I equals 1 to n xi minus x bar squared divided by n minus 1. I'm going to change colors because I hadn't meant to do it in red. Yeah, so notice that this is actually not only a function of obviously your data, but in fact it has some kind of, function of the mean. So this is an important thing, right? Because you might almost think that because your index is n, that it means that your S squared must be distributed chi n with chi squared with n degrees of freedom, but it's not. It's distributed, chi squared with, n minus 1 degrees of freedom. If I don't assume that, mu is known, and I don't think we were told in the question it's known, so I'm not going to assume it's known, right? So this means that we can express the S squared as something that's distributed, your chi squared with n minus 1 degrees of freedom. I'm not going to assume that this is known, that mean is known. So, we're going to lose the degrees of freedom in the estimation of the mean itself, because obviously you need to know the mean to really actually determine the variance with respect to your data, or the estimated variance. Okay, so let's go through this then. First of all, I'm going to use something I know about the sample variance. I know, right, the expected value of S squared is actually equal to sigma squared. It's an unbiased estimator. This is important because remember I said, maybe a few minutes ago, maybe 5 minutes ago, that it is the fact that we're always looking at this, bias variance trade-off, and immediately we have a really nice property of the sample variance in that it becomes an unbiased estimator of sigma, which means that when you're calculating the MSE, as you're asked in the question, at least the first part, the part that is related to the bias itself, is going to be 0. So which means that when I want to compute this MSE of the sample variance, I'm going to think about it in the context of the variance, right? Now, before I answer the question, I'm going to kind of direct your attention to the way the question changes when you introduce this, an estimator for sigma that is a function of n. So you also ask another question to find the MSE of sigma hat squared, which is equal to n minus 1 over n. So it's this ratio of n's times s squared. So immediately you know that if s squared is, right, unbiased, this one can't be, because you have this expression n minus 1 over n, and while this asymptotically, it may actually be unbiased because the limiting ratio of n minus 1 over n is, of course, 1. For finite samples, this actually matters quite a lot, right? This is not the best estimator because in small sample sizes, n minus 1 over n is certainly not 0, right? So immediately we're almost intuitively asking, what he's asking you is like, determine what kind of constitutes a good estimator, and you're going to always consider the bias, right, in relation to the variance, but you're also going to consider the sample size, because I just said that if your sample size is sufficiently large, well, asymptotically, n minus 1 over n is going to 1. So maybe this is a good estimator for large sample sizes, but for small sample size, it's not great. And the way this could be a good estimator for large sample sizes would be if, for instance, the limiting ratio of the variance for this estimator is perhaps, if it is, and in fact, we'll work it out, if it's smaller than the variance you see on typical s squared, because of the variance of the asymptotic thing here is actually smaller, then maybe for large samples, this could be a better estimator potentially, right? So let's have a look and see. So I know that expected value of s squared is equal to sigma squared, which has to insinuate that the expected value of s squared, right, minus theta squared is equal to 0. This is obviously the bias, right? So what does that insinuate? It's going to insinuate that expected value of s squared minus sigma squared is equal to 0, right? So that at least gives us the bias squared is 0. So let's imagine what can happen, right, if we look at the variance. So this is when he says, use the properties of the chi-square distribution to calculate the variance, basically. So right now we know then that the MSE is going to be equal to the variance of s squared, because, of course, we know that the bias is 0, right? So this is going to be equal to, well, I'm going to obviously try to, introduce a couple of things. First of all, let's kind of pause for a second. It's equal to what? Let's pause and make a note here that the variance of something I do know, which is obviously something I can express as a chi. So I know that n minus 1 over sigma squared. Oh, let's make this a bit better. Okay. This looks messy. Okay. So I know that the variance of this, well, I know this is chi, obviously, right? So this is a thing that we know is distributed chi. So let's kind of remind ourselves that this is obviously, this thing here is, chi squared with n minus 1 degrees of freedom, right? So oops. Okay. So I'm going to use this to derive obviously the variance of s squared. Well, first of all, you guys know that variance is a squared operator, right? Which means that if I'm working with things that are constant, when I pull them out of the variance, it's not a linear thing. I have to square everything I take out of the variance because again, it's a quadratic thing, quadratic square, right? So it's going to be equal to, and actually you can see it from the formula of the MSE here, that it's actually a square operator, right? So, you know, we have to square everything that comes out of the actual expression. It's going to be equal to n minus 1 squared divided by sigma squared, right? And times the variance, oh, to the 4, it's going to be squared. To the variance of s squared. So we have this relation here. Now, first of all, I haven't really actually, okay, this is step 1. So pointing out that, you know, we know that this thing is chi is one thing, but we also know that the variance of anything that's chi is going to be 2 times the degrees of freedom, right? Which means that I know, because this thing is distributed chi, that in fact, the degrees of freedom is actually, or sorry, the actual variance is 2n minus 1, because degrees of freedom is n minus 1, right? So this automatically gives me a way that a relation to the variance of S falls out. Why is that? Because that has to imply, right, through obviously cross multiplying and double checking our I's and T's, that the variance of S squared is in fact going to be equal to sigma to the 4 over 2n minus 1. So I'm going to, again, make this look nicer. I apologize. Okay. So now the question we should ask ourselves is, okay, so this is how the MSE is, which means you can see that as n gets very large, your MSE is going to get smaller in relation to how small your variance gets, right? So the question we could ask ourselves is, how is this relation comparable when you look at any other estimator, right? So if you consider any other estimator, one thing you want to look at is among the class of unbiased estimators, for instance, can you get the variance to be smaller than what you see here, basically? Because if you can find any other unbiased estimators, or even one that is asymptotically unbiased for large samples that happens to actually have a smaller variance, it may actually constitute a better estimator than what we've actually seen here. But let's pause that thought and address the second question, because in some sense, we're looking at this, right, when we consider another estimator for sigma squared that has its own features in regards to bias and the variance. Okay, so this is the second question you were asked, right? So you were actually asked, now change the actual properties of your estimator slightly, because now let's make it a limiting ratio of n in regards to n, so as you see here. And what exactly happens to your MSE, right? So first of all, we automatically know that we have to do some work in regards to bias, because now it's not actually 0, right? Because you have this limiting ratio. So now let's compute this. I'm going to change the color. So, so now let's look at bias, because we now know we cannot just say, oh, it's an unbiased estimator. It's not, right? It's going to be equal to the expected value in this context here, expected value, right, of this estimator we have here, which is expected value theta hat squared, right, minus the, and I guess theta in this context here is actually the variance. Okay, so this is actually going to be equal to, well, look and see, right? So first of all, this is going to be equal to the expected value, right, of n minus 1 over n times the expected value of, of s squared, basically, right? Because that's what the limiting ratio is. Now, we know that s squared is unbiased, right? So at least in this way, we can kind of use what we know about the sample variance. We know this is going to be sigma squared, but I'm not going to skip steps, minus sigma squared, right? So is going to be equal to expected value of n minus 1 over n sigma squared, because expected value of s squared is unbiased, minus sigma squared, right? So really, when you say minus sigma squared, you're saying minus n sigma over n, right? Which means it's going to be equal to expected value something that's negative. It's like negative sigma squared over n, right? And this is getting a bit sloppy, so let me redeem it for those who don't like to see messy handwriting. Okay, so this is actually going to be equal to, of course, right, sigma to the 4 over n squared. And so this is what we have. All right. This is certainly not 0. So automatically, we already have this notion of a bias. It's only going to get small as your n is getting small. So like I said, this is asymptotically something that potentially could be a good estimator if we can actually say that our variance is actually smaller, right, in regards to or the decline of the actual variance is smaller by some order than the one that we already have, right? But we certainly know that S squared is actually an unbiased estimator, right? And in fact, I actually think that it is not the one with the minimum variance. So I think the MLE might have minimum variance, but it's not unbiased, right? So yeah. Anyways, let's have a look and see what the variance tells us. So the variance is going to be equal to, well, it's going to be equal to, again, we're going to manipulate this note, the things we know about, you know, the chi-square distribution, and even what we know about S squared, because we're going to use what we saw in the previous question. All right, so we have the variance of n minus 1 over n times S squared, right, which is going to be equal to, well, I can pull out, of course, right, the n minus 1 over n, it becomes just a ratio of n's, but remember, we have to square this because, of course, we're working with a squared operator. So we have n minus 1 squared over n squared, right, times the variance of S squared, which we actually just solved for in the previous question, right? So this question becomes a lot easier when you saw the previous one because things fall out, right? It's going to be equal to n minus 1 squared over n squared. And we know that the variance is actually equal to, the variance of S squared is actually, you know, 2 sigma to the 4 divided by n minus 1, right? So it's going to be a cross canceling out of, you know, the n minus 1s. You're going to end up with something that looks like this. So 2 sigma to the 4, right? And I guess times this limiting ratio of n minus 1 over n squared, right? So don't forget the squared in the bottom. What is interesting to see, right, is that this limiting ratio is something that's like looking almost like 1 over n, right? Because obviously n minus 1 over n, well, that's the same thing as saying, you know, to be just a little bit pedantic here, it's like n minus 1, it's like n. I'm gonna erase this. It's like the following. So we have something like, let's change the color to make it nicer. So we have n over n squared, right? Minus 1 over n squared. And so obviously this falls off to 0, right? And the limiting, this goes to 0 faster than this does because n over n squared is like 1 over n. And obviously the limiting ratio is declining slower than 1 over n squared, right? But overall, this ratio, if in fact this whole thing is, you know, of order 1 over n, which is actually declining slightly faster than the previous estimator, which means that, and like I said, I don't believe that S squared has minimum variance, right? I think the MLE, I think the actual minimum variance is actually not divided by n minus 1, but divided by n. So the variance is not actually the smallest, right, in relation to S squared. And so we can see that this one might actually fall off faster in the variance than the previous one. Let me just confirm that it is of order. Yeah. So the rate of the variance is actually smaller. That you can make the variance smaller here for large samples because it has a steeper decline in n, but it's unbiased, or sorry, it's biased, right? So when you have finite samples, you may not want to necessarily use this estimator. right? If you're looking for something that actually is a non-biased estimator of sigma squared. So asymptotically, it does a pretty good job for large sample size, but for finite samples, we are definitely not necessarily tickled with this particular estimator potentially, right? So that's the end of this tutorial. I think the next one I have is March 22nd. So next week, some other TA will take it away. I hope this was helpful. And if you have any questions, you can ask in the discussion board. Thanks.